Hey guys, today we are going to continue in chapter 5. We are finishing 5.2. We're on page 227 in your workbook. And you're also going to want to grab your power chart because we're going to need it. It's going to come in handy. So today's lesson is about operations of radicals. Operations means that we're going to add, we're going to subtract, we're going to multiply, and we're going to divide, but really simplify quotients involving radicals. So we're going to start with adding and subtracting radical expressions. In order to add and subtract radical expressions, we need to have something called like radicals. Like radicals have the same index and the same radicand. So only like radicals can be combined with addition and subtraction. So if you forgot what those parts are called, the index is like whatever root it is, not like, it is. It's whatever root it is. And then the radicand is the number that's under the radical. So the only way I can add or subtract radical expressions is if I have the same index, the same radicand. So here's an example. Let's say I had the cubed root of 2 plus the cubed root of 2. They have the exact same index. They have the exact same number in the radical. And what you're going to do is you're going to treat each part like it's an x. So you're going to treat this whole part like it's an x. And then you're going to treat the second part like it's an x. Because if I just had x plus x plus x equals 2x. Well, right now I have this cubed root of 2 plus one more cubed root of 2. That means I have 2 cube roots of 2. Now, if you look at this first example, none of these have the same radicand, and only 2 of them have the same index. So that's the problem. We need like radicals. Now, if we don't have them, we're going to try to make it. So if we don't have like radicals, we're going to simplify to see if we can. So we're going to simplify each radical. All right, so I'm going to need some space. I'm going to scroll. Okay, so I've just recopied the problem. The cubed root of 2,000, let's go to my perfect third powers, is 2,000 in perfect cube. It's not on this list, so it's not. Okay, so then let's try to simplify. Will any of these perfect cubes divide evenly into 2,000? I'm looking. Oh, look, 1,000. 1,000 will go evenly into 2,000. So I can rewrite this as the cubed root of 1,000 times 2. The square root of 2 is already simplified. You can't really simplify the square root of 2. And then the cubed root of 128. So is 128 a perfect cube? No, 125 is, but not 128. So will any of these other numbers, other cubes, go into 128? So I'm grabbing my calculator. Let's see, 128 divided by 64. 2, yeah, 64 goes into it twice. So I can rewrite the last one as the cubed root of 64 times 2. So then if I simplify everything, the cubed root of 1,000 is 10. So I have 10 cubed root of 2 plus the square root of 2 plus, and I need to know what the cubed root of 64 is. 64 is right here. Cubed root of 64 is 4. So plus 4 cubed root of 2. So then I need to see, do I have any like radicals? Well, let's see. I need to have the same index and the same radicand. So I have a cubed root of 2 and another cubed root of 2. So that makes these two terms like radicals. So if I have 10 cubed roots of 2 plus 4 cubed roots of 2, that's 14 cubed roots of 2. Square root of 2 has a different index, so I will just have to leave it separate. So 14 cubed root of 2 plus the square root of 2. Part B is another example with square roots. So again, these are all square roots, and I can tell they're square roots because there aren't numbers. There are no indices written, but they are understood to be a 2. All the radicands are different. I have a 20, a 600, and a 125. So if I want to try to see if they become like radicals, I need to simplify each radical expression. So let's see, I'm looking for a perfect square that goes into 20. I know 4 goes into 25 times, so I can write that as 4 times 5 minus, I know 100 goes into 600, so 100 times 6 minus the square root. 25 goes into 125. I think 5 times, just double checking. Yes. Then I'll simplify each part. The square root of 4 is 2, so 2 square root of 5, minus the square root of 100 is 10, 10 square root of 6, minus the square root of 25 is 5, square root of 5. Now, do I have any like radicals? They're all square roots, so they all have the same index, but I also need like radicands. Square root of 5, square root of 5. So then I'll combine a positive 2 plus a negative 5 square roots of 5 to get negative 3 square roots of 5, and then just bring down the 10, minus 10 square root of 6. Now let's move on to multiplying radicals. Multiplying radicals is going to feel very familiar. In this example, example 5a, we are multiplying two binomials. So you'll multiply this in the same fashion that you would multiply x plus 2 times x minus 1. You can use the same method. I like to distribute. So if I were to multiply these two binomials, I would distribute the x to the x to the negative 1, 2 to the x, and 2 to the negative 1. Well, I'm going to do the same thing here. I'm going to distribute x times x. X times x is x squared. X times the square root of 10 is plus x times the square root of 10. You just write it out. X times the negative square root of 10 minus x square root of 10. And then the square root of 10 times the square root of 10 is negative square root of 100. And the square root of 100 is 10. So x squared. Ooh, what's happened here? Positive x squared of 10, negative x squared of 10. They have like radicals. And a positive x plus a negative x is 0, so those cancel out. And square root of 10 is minus, or square root of 100 is 10. So x squared minus 10. And for the second one, we will distribute just like you normally would with an x problem. Now, when you're working with radicals, here's what I like to remember whenever you're multiplying. You can multiply what's on the inside. I'm misspelling words all over the place. You can multiply whatever's on the inside. I did it again. Inside times the inside. And you can multiply the outside times the outside. But I do need to modify that first statement. You can multiply the inside times the inside as long as you have the same index. So on part B, I see where all the radicals are square roots, so I can multiply the inside part. Now, you do not multiply an outsider times an insider. So if I have to multiply the square root of 6 times 5, that 5 is just going to stay out front. The 6 is going to stay on the radical. So square root of 6 times 5 is 5 square root of 6. And we usually write the 5 in front so it doesn't look like you have a 5 underneath the radical. It just clears up any ambiguous writing there. And then square root of 6 times square root of 3 is plus the square root. Since the 6 and 3 are both under a square root, I can multiply that together, get 18, and then I'll simplify from there. So 5 square root of 6. Now 18 can be simplified because I can write it as the square root of 9 times 2. So 5 square root of 6 plus the square root of 9 is 3, 3 square root of 2. And now I've got the square root of 6 and the square root of 2. They are not like radicals, so I will leave those totally separate. Now let's talk about simplifying quotients involving radicals. And to do that, we go through a process calling rationalizing the denominator. You need to rationalize the denominator when a radical or a rational exponent, which is the same thing as a radical, it just doesn't look like it, is present in the denominator. Now in Algebra 2, it's accepted in Algebra 2 to say that it's improper to leave a radical in the denominator. So in Algebra 2, you learn how to rationalize the denominator. In pre-calculus, you'll also have to rationalize the denominator quite a bit. But then when you get to calculus, sometimes you'll have to rationalize the numerator. And so what that means, rationalizing the denominator or rationalizing the numerator, that just means get the radical out of that side of the fraction. But in Algebra 2 and in pre-calculus, there's a huge push and a huge emphasis on rationalizing the denominator, meaning there are no radicals left in the denominator. So there's a process for doing that. And by the way, that helps everybody stay consistent. It helps us all end up with the same answer when we simplify. So just know in Algebra 2 and in pre-calculus, you're going to be stressed. We are going to stress to you to rationalize the denominator. So we've got to get rid of this radical down here. The way we do that whenever there's a binomial. Remember, a binomial has two terms. So you're looking at something like 2 minus a square root. Two terms. You're going to multiply. Here it is right here. Multiply by the conjugate of the denominator. So the conjugate is where so if I have a plus b, its conjugate would be a minus b. You just change that symbol in the middle. Everything else stays the same. So if I had 2 plus the square root of 5, its conjugate would be 2 minus the square root of 5. So and when it says multiply by the conjugate, you need to multiply the numerator and denominator. Because, tell you what, let me write this down. So the conjugate of 2 minus the square root of 3 would be 2 plus the square root of 3. You need to multiply by that in the top and also in the bottom. All right, now why do I have to do it to both? Because we still have to follow all the rules of math. I can't just take this first expression and change what it means by just multiplying it by whatever I want to. But I can multiply it by 1 because anything times 1 is going to be itself. Now I'm going to multiply by 1, it just won't look like 1. 2 plus square root of 3 over 2 plus square root of 3, that's 1. This is equivalent to 1. So I'm not going to change what the original problem means. I'm just going to change the way that it looks. Kind of like if you wear makeup or if someone close to you wears makeup, it doesn't change who they are. It just changes what they look like. So this is like the makeup of math. Okay, so let's do that. I'm going to multiply in the numerator 5 times 2. And again, the way you multiply fractions, multiply straight across. So 5 times 2 is 10. 5 times the square root of 3 is plus 5 square root of 3. Negative square root of 2 times 2 minus 2 square root of 2. And then negative square root of 2 times the square root of 3 is negative square root of 6. Doesn't look too pretty now, does it? But let's see what happens in the denominator. 2 times 2 is 4. 2 times the square root of 3 is plus 2 square root of 3. Negative square root of 3 times 2 is minus 2 square root of 3. And negative square root of 3 times the positive square root of 3 is minus the square root of 9. Take a step back and see what happened. Positive 2 square root of 3 minus 2 square root of 3, those cancel. And then the square root of 9 is really 3. So let's see what this all simplifies to. In the denominator, 4 minus 3 is 1. So really I just have the numerator. And there's nothing to simplify a numerator, so 10 plus 5 square root of 3 minus 2 square root of 2 minus the square root of 6. And I can't combine any of those radicals because they don't have the same radicand. Now the whole thing's over 1, but we don't if you have a fraction that's over 1, you don't have to write that 1. So I'm going to erase the denominator part and say, here's my answer. Let's do another example with variables this time. So I'm going to follow the same procedure. I'm going to multiply by the conjugate. So I'll change this minus in the middle to a plus. So I'm going to multiply by 1 plus the square root of x over 1 plus the square root of x. So let me grab another color. Negative 4x times 1, negative 4x. Negative 4x times the square root of x is minus 4x square root of x over, in the denominator, 1 times 1 is 1. 1 times the square root of x is plus square root of x. Negative square root of x times 1 is minus the square root of x. And square root of x times square root of x is negative square root of x squared, which simplifies to just be x. The square root of x squared is just x. So then if I write, oh look, and the positive square root of x, negative square root of x, those cancel. So it looks like I've got 1 minus x in the denominator. So my answer, negative 4x minus 4x square root of x all over 1 minus x.